calculate the electrostatic potential energy for bringing a charge into a field. Let's now calculate the work done to move a charge from infinity to a point x sub I. Equation 4-75. Since phi of x sub I equals the sum from j equals 1 to n minus 1 of q sub j over the absolute value of x sub I minus x sub j, we have w sub I equals q sub I the sum from j equals 1 to n minus 1 of q sub j over the absolute value of x sub I minus x sub j. The total potential energy is then
Equation 4-76. Or, for continuous source, charge density. Equation 4-77. From the last form, substituting Poisson's equation gradient squared phi equals 4 pi rho. Equation 4-78. The energy density can be seen to be Equation 4-79. Capacitance. Suppose you have a system of n conductors, each with charge q sub I and at potential v sub I, and arranged in some fixed geometry in otherwise empty space. We know from the linear superposition properties that we must be able to write the potential at conductor I in terms of a sum over all of the conductor charges, each with a fixed factor, dependent on geometry of conductors and their placement.
Equation 4-80, which is inverted to have Equation 4-81. The C sub I values are known as the capacitances, while the C sub ij with I is not equal to j are known as coefficients of induction. To get the capacitance of an object, hold all other, nearby, conductors at zero potential, ground, and measure the charge present when the conductor is held at unit potential. To determine the work required to charge a conductor, a capacitor, we have W equals 1/2 the sum from I equals 1 to n of q sub I v sub I equals 1/2 the sum from double struck ij to of c sub ij v sub I v sub j. Equation. For -82.
Example 4.2. Consider the flux at an element of an irregular enclosing surface. Solution. Since the flux at the surface element of each solid angled division of the surface may be given by d sub r equals q divided by 4 pi r squared, and since the flux impinges upon a surface described by the surface ds sub up tac equals r squared d omega, we have. See the next equation. With 4 pi sterardians. We also have. See the next equation. Thus, see the next equation.
Example 4.3. Derive the continuity equation from the following Maxwell equations. See the next equation. Solution. We have. See the next equation. Thus, see the next equation. Example 4.4. Dirac delta function as improper limit of Gaussian function. Solution. Consider the three-dimensional Gaussian. See the next equation. Let's take the delta function to be the limit. See the next equation. In generalized coordinates du over u, dv over v, dw over w, as alpha goes to 0, we are only interested in the infinitesimal length element. ds squared equals du over u squared plus dv over v squared plus dw over w squared, and see the next equation.
Thus, d of alpha semicolon xyz equals delta of u prime minus u over u delta of the fraction with numerator v prime minus v and denominator v delta of w prime minus w over w equals delta of x minus x prime. And delta times x minus x prime equals u v w delta times u prime minus u times delta times v prime minus v times delta times w prime minus w. Example 4.5. Let's now consider spherical and cylindrical delta functions. A. For spherical coordinates we have the metric. See the next equation. Thus u equals 1 v equals 1 over r w equals 1 over r sin theta. And we have delta times x minus x prime bold equals 1 over r squared sin theta delta times r prime minus r times delta times theta prime minus theta times delta times phi prime minus phi.
Suppose there is charge q over the spherical shell. Then, in terms of delta functions, see the next equation, is the charge distribution, for which we have total charge q equals the integral from 2 of rho of x. Solving for the form of a, see the next equation. Thus, rho of x equals q over 4 pi r delta times r minus r. B. For cylindrical coordinates we have the metric. See the next equation.
Thus, see the next equation. Suppose there is a charge per unit length, lambda, on a long cylinder, radius b. See the next equation, where lambda equals q over z equals a b 2 pi a equals lambda over 2 pi bq equals lambda z. Thus, see the next equation.
Example 4.6. Consider three spheres of radius a with total charge question. 1. Conducting. 2. Uniform charge density. And 3. Spherically symmetric charge density. Varying radially as r to the nth power where n is greater than -3. Find the behavior of the electric fields inside and outside the sphere for I, 2, and 3, with n equals plus or minus 2. Solution. Part I. The integral from 2 of gradient dot e times dv equals the integral of rho double struck dv. The contour integral from s2 of e dot n equals 4 pi. The integral from v2 of rho dve of 4 pi r squared equals 4 pi q times outside. For the conducting sphere, we know E equals 0 inside the conducting region, r is less than a. While outside the conducting region, e.g. r is greater than a, we have.
See the next equation. Let's now consider r equals a. We have the junction condition and dot e sub 1 minus e sub 2 equals 4 pi sigma, with e sub 2 equals 0 on the inside. So, E equals 4 pi sigma r equals the fraction with numerator q and denominator a squared r at the surface, since E sub 1 cross n equals 0, and q equals 4 pi a squared sigma. Part 2. The contour integral from s2 of e dot n equals 4 pi of the integral from v2 of rho dv goes to sign with r is less than a over at 4 pi of r squared. E equals 4 pi of 4/3 pi of r cubed rho.
Inside the sphere we have E equals the fraction with numerator r and denominator a cube times qr. Outside the sphere we have E equals q over r squared times r. 3. Need to get charge density. Starting from the form rho of x equals a r to the nth power. See the next equation. So, we have rho of x equals n plus 3 times q over 4 pi r to the nth power over a to the nth power, the fraction with numerator 1 and denominator a cubed, left arrow r is less than or equal to a. Working with the usual. The contour integral from s2 of e dot n equals 4 pi the integral from v2 of rho dv.
We get for r is less than or equal to a, 4 pi r squared times the absolute value of e equals 4 pi q r raised to the n plus 3 power over a raised to the n plus 3 power times th of us times the absolute value of e equals q r raised to the n plus 1 power over a raised to the n plus 3 power. While for r is greater than a, we simply have the absolute value of e equals the fraction with numerator q and denominator r squared. Let's now consider the specific cases of n equals plus or minus 2. Both will have e equals the fraction with numerator q and denominator r squared times r for r is greater than a, while for r is less than or equal to a we have the absolute value of e equals q over a r for n equals -2 and the absolute value of e equals the fraction with numerator q r cubed and denominator a to the 5th power for n equals 2.